Hi, everybody. This is Straight A Programming. This is a continuation of data structures in Java. Today, I'm going to talk about linked lists, um, specifically singly linked lists. And so basically, I create a singly linked list node class, and this creates new instances of node. And so with a linked list, you got value and next. That's the two things you keep track of in a linked list. And so with the node, um, the constructor is going to initialize the value at the node and the the node that it's pointing that a node's pointing to. So in a singly linked list, they're pointing to a next node. And so that's how you keep track of where everything is in a linked list, is with the next. And so, there are two private variables, object value, and we're just going to deal with numbers in this tutorial, and the next node. And so I have getters, get the value at the node, get the next node from a node, and set the next node. And those are nodes. Okay, so to make it easier to manipulate the nodes and traverse over a linked list, because a linked list contains these nodes. But to make it easier to work with a linked list, I create a linked list class to manage the nodes in the linked list. Okay, so in the linked list class, there's two private variables, head and tail. The head is like the first item in the list, and the tail is the last item in the list. And at the start, head's pointing at tail. So anyway, in the constructor, initialize head pointing at the tail, set next. So I use the singly linked list node function I just showed you to have the head pointing to the tail. So basically, it's an empty list, linked list. Those are referred to as sentinel nodes. Head and tail are sentinel nodes. That's like a name they give it. Anyway, so I set them both to null. And if there is so when the linked list is created, you can populate the initial values if the start list is given. If start list is not null, then I can start inserting. This is one of the functions down here. It inserts the value at each node, each object value. There's a string representation of the linked list. I'll show that in a second. You can see it right here. So this right here returns the number of elements in the linked list. It just reaches all the nodes until it gets to the tail. And this is a standard algorithm in linked list, while current get next is not equal to the tail to the end. And so it returns the length, and this is to see if the list is empty. And that's convenient to have in the linked list to find out real quickly. That just returns a Boolean. So I have some sample functions that you can do with a linked list. This is insert a node at the beginning of the list. Insert start, and then that's the value that's going to. So you just create a new node, and you insert that node with that value right here. Creates an instance of the singly linked list node class, value and the node. And this is the next value. This is the next node. So you have the sentinel head is pointing to the new node, and this new node is going to be pointing to what head was pointing to. So if head was pointing to tail, now the new node is going to be pointing to the tail. And now insert in the back, you insert it from the tail side instead of the front side. So just the same as before, you create a new node for the node class. You iterate to find the node before the tail. The new node pointer is set to point to the tail. It's this new node you create with the singly linked list. And the current node pointer points to the new node. So it's the same algorithm. And then you set the new node set next, and list.tail. And the current place, the current set next, which is pointing to the tail, is now going to point to the new node, which is pointing to the tail. Standard algorithm, this is like some normally stuff you see. And this is going to be inserting a value at a specified index in the linked list. So before it was insert at the start and insert in the back. This is going to insert somewhere in the middle. And technically you can use this to enter start and back if you wanted to, like index was 0. You can enter, that'd be like insert at start. But this is more for using inserting something in the middle of a linked list. So you just validate the index that they want because you're passing in an index and the value. Initialize the current node to point to head, and you just start traversing until before the specified index. So say you want to end up inserting the new node at the index. So you got to stop before there, because then once you insert it there, it's going to be the index that you want. And so it just moves the current node pointer to the next node. New node's next pointer points to where our current node points to. See there is the new node. And so you got the value and the current dot get next. And then current set next is going to be the new node, because you're inserting the node at the spot you stopped at. This is remove value at node. So you do a valid index validation, and then you initialize the current to point to head, and then you iterate it just like before. Iterate through the linked list. Iterate through all the nodes, and you identify the node to remove by setting the node current is pointing to. Current's next pointer skips the node to be removed to point to the node next to it. Okay, so basically at some point here, the next node that you're trying to remove is pointing to the next node, and current's next pointer is also pointing to the same node. That's what's going to happen. So you're going to have two nodes, the node to remove and the current node pointing to the same node. So at the very end of the node to remove, you need to make sure that you set that to null, or you're going to have two pointers pointing to the same node. You're going to have like a dangling node if you don't do that. So that's how you kind of like get rid of it. You just got to make sure your pointers that are meant to be null, you need to null them out. So somewhere in memory, this node still exists, but it doesn't exist in this linked list anymore. But in memory, it's still there on the hard drive. So anyways, so that's important right there. That ends up causing problems. So you got to make sure you're managing your memory correctly. And this is delete all the values, given values. Say I pass in a value here and I want to delete the value, all of them. So I set a Boolean value removed to false, just so I know that if false gets returned, the value was never found in the linked list, and remove or no value was removed. Really, that's a different function where you're searching for a value, and you return a Boolean. This just says, false means that the value was never removed, which indirectly says it was never there, as long as it's coded correctly. So I just, like before, send the current to pointing to the head. I traverse the nodes while the next is not the tail, and I just remove the value. And I use a similar, almost the same algorithm as up here, to where I have the current pointing to the next node over, and then I have the node to remove these values that were passed in. I set those to null, and then I'll put remove to true, and that's what gets returned down here. The true if something is removed, and right here is like if the values while the value is not found, it's just going to keep traversing. Okay, so all right, so this is the main function I wanted to test. I wanted to show you an example why modularity is really important. So remember, I created a singly linked list node class that deals with the nodes, and I created a linked list class to manipulate the nodes with all the functions. So if when I so as you can see, modularity is very important. Both of these linked list class. So if in main, I'm able to work or any other outside of the linked list class, I'm able to work the linked list like this up here. The code's real simple. The linked list abstracts away all the details of the nodes. Whereas without this linked list class, this is what this would look like if I had to deal with the individual nodes. It's going to look like this. I've got to create all these different nodes every time I want to do something. It's just a mess. So I want to show you how important, why that is important. That creates two separate classes for linked lists here. You got the linked list to manage the nodes and the nodes itself. Modularity is important in object-oriented programming, especially when the code gets complicated. So basically the first function, let's okay, so in this first I first test the insert at the beginning. So I just create a linked list object, and I insert a few values. That's before. Just compile, and I'm gonna run it. So at the very top, it's just it inserts. I just enter three values. So 10 gets inserted, 20 gets entered, 30 inserted, and it inserts it at the start. So it gets pushed to the back. So 10 ends up being the tail. And then that's the output. The length is 3. Is it empty? False. Not really complicated tester functions, just making sure they work for now. This is like insert value at the index. So I'm going to use I'm going to create a new list and just at the start. So it's going to be very similar, 300, 200, 100, just like before. I'm going to print it out, and then I'm going to insert the value. I'm going to call the function at index 2 and put the value 3. So it's very easy to see, 0, 1, 2. And as you can see here, what it does when this 3, I got to create a pointer to where 200 was pointing to 100 up here. I got to make 200 point to 3, and then 300 pointing to where 200 was pointing to. Okay, that's how that works. The length is 4, and threw an exception there too to test that out, and invalid index. Okay, so and this is remove value. The next one, it's similar to the previous one, like insert. So I use the same list I just used with the 4 values right here: 300, 200, 3, and 100. So let's see where I call. Oh, so I just remove. I move the value at index. I move the node. That's actually there's better names. Remove value. It's actually I'm removing the node at index 1. So basically, if it's 300, 200, 100, 200 is going to get removed. And so when you remove 200, the algorithm is going to stop there. And where it's pointing to 3. 200 is pointing to 3. So I make the 300, I make that point to 3, right? And then 200, which is still there somewhere in memory, is still pointing at 3. So you got 300 pointing at 3 and 200 pointing at 3. I just have 200 pointing to null to get, so that no longer is part of the linked list anymore. You got to remember to null that out. And so the length's 3, and I threw in another exception, test that out. And I delete values. So I created, I didn't write over the list. That's right. I inserted them at the start. So you already started with 300, 3, and 100. And I inserted these at the start. So I just added to the previous list. So there's the initial list, and I pass in the value 100 to remove, and it's going to remove all the values of 100. So there's 8 elements in there. I have it right here, and I remove all the hundreds. I'm testing it out, and I print it out again, and all the hundreds are removed, and there's only 4, and then it says it returns true when any nodes, at least 1 is removed. I could return the count 2 if I wanted to, but I just wanted to do something really quick. And there's other functions you can do with this. But this is a singly linked list node. Singly linked list in Java. This is a standard data structure that you must know. Thank you very much. Like and subscribe.